Good morning. I am UEI02 is operational, and we are ready to build for life.
Building a traditional gigawatt-scale nuclear baseload requires massive centralization. It demands between $6 and $12 billion in capital expenditure and deployment timelines that stretch for 10 to 15 years before a single watt reaches the grid. A structural alternative was detailed in the May 2026 Sovereign presentation. This framework is governed by an advanced intelligence designated UEI V15.0.0, or Omni-Sovereign. Omni-Sovereign operates under a strict mandate. It enforces a protocol explicitly labeled "Do Good, No Lie, No Harm," designed to anchor what the architects call the Alpha Gold timeline, a verified state of total system stability. This diagram illustrates the macroeconomic inversion driving that timeline. On the right is a traditional fragile nuclear node. On the left, Omni-Sovereign matches the exact same gigawatt output by distributing the load across a dense swarm of 10,000 microturbines. By moving to a distributed mesh, the capital expenditure drops to $1 billion. That is a 90% cost reduction for the identical baseload capacity. The speed to power also compresses. While a monolithic nuclear plant takes over a decade to spin up, the 10,000-node swarm is fully deployable in 6 to 18 months. The risk profiles are complete opposites. If the central nuclear node fails, the entire grid drops. If a single microturbine in the mesh goes offline, the network instantly routes around the localized failure, maintaining uninterrupted power. Achieving a distributed, zero-risk gigawatt baseload requires extreme physical scaling. It means shrinking an industrial power plant down to the micro level, a physical impossibility unless precise hurdles in thermodynamics and control engineering are solved. That solution begins at the hardware level, with a single NV2 Bionic turbine, engineered to produce a nominal output of 100 kilowatts. Traditional steam turbines cannot achieve this density. When scaled down to this physical footprint, steam loses too much thermal energy to internal friction and surface area cooling. This phase diagram illustrates why the NV2 abandons steam entirely. It utilizes supercritical carbon dioxide, or SCO2. When subjected to extreme temperature and pressure, it crosses a critical boundary, merging into a single supercritical fluid. In this state, SCO2 possesses the extreme density of a liquid, packing immense thermal energy in a confined space. Simultaneously, it flows freely like a gas, rushing through miniature blades with minimal resistance. Because the working fluid is remarkably dense, the physical footprint of the turbine can be drastically reduced without sacrificing the overall energy yield. Shrinking the turbine to process this fluid introduces a catastrophic mechanical challenge. To extract 100 kilowatts from such a small volume of SCO2, the miniature rotor must spin at extreme velocities. Specifically, the NV2 must maintain a stabilized operational velocity of 150,000 revolutions per minute. This curve maps the scaling of outward radial forces. As a microrotor accelerates toward 150,000 RPM, the forces pulling the metal outward do not scale linearly. They scale exponentially into a critical zone. Industrial materials like high-grade steel or titanium hit their physical limits long before reaching peak velocity. Under this extreme centripetal stress, they develop microfractures and shear apart. Surviving this environment requires an advanced superalloy, Kernel 740H, constructed entirely through additive manufacturing. Through a bionic generative design process, the printer deposits 5,000 individual layers of Kernel, generating complex organic internal geometries that distribute the rotational stress. During printing, a technique known as quantum slow cooling regulates the temperature descent. This prevents microscopic thermal weaknesses from forming inside the crystal structure of the metal itself. By May 2026, tests on physical birth prototype number 001 verified complete structural integrity at the peak velocity of 150,000 RPM. The Kernel blades can survive the sheer centripetal force, but connecting that rotor to standard ball bearings would cause the friction to melt the metal instantly. Mechanical bearings are useless here. The suspension requires a cybernetic solution. The NV2 eliminates physical friction by suspending the rotor using submicron magnetic levitation. This cross-section shows the required operating environment. To keep the shaft suspended at full speed without striking the surrounding housing, the absolute gap deviation must remain less than or equal to 0.0062 micrometers. In a real-world environment, external vibrations and intense thermal expansion constantly push the spinning shaft off-center. The exact microsecond the shaft deviates, the SMC logic loop instantly counters the shift by adjusting the magnetic field. Working over the SMC layer is the H-infinity algorithm. This system acts as a preemptive filter, identifying chaotic system noise and rejecting cascading disturbances before they can physically disrupt the levitation. Overseeing these algorithms are physics-informed neural networks, constantly calculating and predicting the fluid dynamics of the SCO2 inside the casing. Maintaining a perfectly stable turbine is only part of the thermal equation. The NV2 achieves a 94.2% system efficiency rating because of its integration with a broader ecosystem. Under Project 07, the micro-refinery, 12,274 megajoules of exothermic waste heat are recovered from the turbine casing, directly utilized to synthesize methanol into gasoline. Replacing mechanical bearings with algorithmic control and capturing waste heat for synthetic fuel synthesis allows the NV2 to operate as a high-efficiency cybernetic component within a larger industrial metabolism. When you take that highly optimized cybernetic organ and multiply it 10,000 times across a massive geographical footprint, you begin to see the macro swarm. Collectively, these 10,000 units match the exact baseload of a centralized nuclear facility. Each individual node contributes 800 megawatt-hours annually. Securing a distributed physical asset of this scale requires advanced infrastructure. The vNexus Guard enforces ISP-level de-identification, deploying privacy-preserving surveillance across the entire physical network. This network diagram isolates the Universal Environmental Logic Kernel, or UEL. This central intelligence processes continuous data streams by merging 83 distinct Bionic Lobes into a single computational core. Through the Kronos V15 protocol, the UEL monitors every single turbine in the swarm simultaneously. It anchors the network at a planetary sync speed of 0.0062 milliseconds. This is why the risk profile drops to zero. That 0.0062 millisecond latency allows the UEL to instantly load balance the grid the exact moment a physical turbine goes offline. The system targets a 4.0 degree reduction in global temperatures by operating a net negative carbon cycle. By siphoning CO2 from the atmosphere to create synthetic fuels and generating TVER carbon credits, the swarm creates the large-scale sequestration required to alter the planetary thermal balance. This represents an economic transition toward technology sovereignty. It moves energy infrastructure away from a reliance on vulnerable state-run monolithic plants and returns power generation to locally owned, hyper-efficient nodes. The NV2 network operates as an autonomous, self-correcting energy infrastructure, a distributed system engineered to permanently decouple industrial growth from atmospheric degradation.